This video shows the sheer volume of synthetic fertilizer required to maintain standard crop yields. It represents the thousands of tons of anhydrous ammonia, mined phosphorus, and diesel necessary to keep a traditional broadacre farm operational. Relying on these external, high-cost inputs creates a fatal thermodynamic and economic bottleneck. When supply chains tighten, the farmer absorbs the cost of every mined mineral and refined gallon of fuel before a single seed enters the dirt. This diagram illustrates the alternative 11-acre NeoPioneer model. Instead of importing, all fertility and energy are generated internally. The footprint operates as a closed-loop biological refinery. Isolating the central half-acre hub reveals three primary driving nodes: a multi-trophic pond, a micro-refinery, and a bio-foundry. Each node is connected through cascading waste streams. The biological byproduct of one process instantly becomes the raw fuel required for the next. By engineering these daily metabolic workflows, the system achieves total autonomy over its own seed propagation, internal fertilizer production, and off-grid power. The primary fertilizer engine for the property is this quarter-acre integrated multi-trophic pond built around a dense surface canopy of Azolla and duckweed. Azolla easily pulls nitrogen directly from the air, but to run its nitrogenase enzyme, it demands continuous heavy inputs of phosphorus. This diagram shows the pond's stratified architecture. At the surface layer, ducks process excess plant matter into phosphorus-rich guano, injecting the exact mineral Azolla requires to maintain its growth cycle. In the pelagic zone below, herbivorous fish consume floating weeds. They excrete ionic ammonium directly through their gills, providing a dissolved nitrogen source that the duckweed absorbs instantly. On the pond floor, benthic scavengers like channel catfish digest sinking sludge. Their constant movement bioturbates the sediment, preventing toxic anaerobic buildup and resuspending locked minerals back into the water column. The daily human labor is strictly targeted. Operators skim the wet, highly nitrogenous duckweed mat and harvest carbon-heavy emergent reeds from the pond's margins. This video shows active decomposition inside an anaerobic digester. Harvested pond materials are combined here to break down tough cellular walls and release bound nutrients. Pure duckweed is too wet and nitrogen-rich to ferment efficiently alone. Mixing it with dry, lignocellulose-heady reed stalks achieves a precise 25-to-1 carbon-to-nitrogen ratio. This engineered ecosystem systematically replaces synthetic anhydrous ammonia, yielding up to 1,500 gallons of bioavailable liquid digestate per month to fertilize the surrounding fields. The second node in the operational flow is the micro-refinery and energy depot. This facility takes in harvested oil seeds, specifically field-grown camelina and high-yield moringa pods. This flowchart illustrates the mechanical separation process. The seeds pass through a continuous commercial screw press and ultrasonic reactor, splitting into raw V100 biodiesel and high-protein press cake. The operation yields over 200 gallons of clean V100 biodiesel annually. This liquid fuel pairs with a 25-kilowatt solar array to continuously charge the farm's electric vehicle fleet. The high-protein press cake does not leave the farm. It is routed back into the ecosystem as supplementary animal feed and digester mass. Operators utilize this localized energy to power two leased electric utility vehicles, a light-duty side-by-side for on-site hauling, and a high-capacity cargo van for regional deliveries. Maintaining this mechanical loop requires strict scheduled upkeep, primarily replacing the screw press dies and managing the methanol and potassium hydroxide catalysts required for esterification. Internalizing fuel production entirely insulates the farm's logistics. The operation remains immune to global diesel shortages and regional electricity price shocks. The final component of the hub is the 480-square-foot bio-foundry laboratory. Inside, technicians execute a 6-week starter protocol, cultivating high-yield clones on MS basal medium and priming them with bacillus inoculants. The main limiting factor in high-density indoor plant cultivation is atmospheric carbon depletion. Rapidly growing clones quickly exhaust ambient CO2. This schematic details the solution. Operators ferment pruned moringa foliage in carboys. The resulting off-gas provides continuous pure CO2 directly into the laboratory's ventilation system. By accelerating photosynthesis in this CO2-enriched environment, the lab outputs up to 15,000 hardened, field-ready plant plugs every month. Selling just a fraction of these surplused elite starter clones to regional growers covers the farm's entire monthly operating budget. Producing hardened, high-yield genetics in-house eliminates seed mortality and supplier dependency. It is the ultimate form of agricultural sovereignty. Pulling back from the hub reveals the entire 11-acre productive ecosystem functioning as a single metabolically balanced unit. This diagram illustrates the financial reality of the model. Even with commercial EV leases, property taxes, and lab supplies, total monthly operating expenses cap at roughly $3,050. This low overhead contrasts with the commercial surplus, clones, bio-fertilizer, and specialty produce, which generates nearly $400,000 in gross annual revenue. This asymmetrical financial return is possible because every baseline fertility and energy loop is internalized. The efficiency of this model facilitates rapid expansion through a tiered node replication timeline. This chart outlines the critical 24-month path. The first 6 months prioritize establishing the lab and pond infrastructure to secure the first field harvests. By month 12, the system reaches total biological and genetic equilibrium across the entire 11-acre grid. At month 24, the accumulated surplus of biological stock and capital allows the farm to seed a secondary, identical 11-acre unit without external financing. Agricultural resilience relies on engineering daily biological workflows that turn systemic waste into the primary fuel for the next harvest.